Now that we know about gradients, there is another concept that is related to them that can be acquired quite easily, and that concept is contour lines. A contour line, also isoline of a function of two variables, is a curve along which the function has a constant value, so that the curve joins points of equal value. There are very interesting relationships between the gradients and the contour lines. When you go hiking, it is often useful to look at a contour map to give you an idea of the level of the land. These maps display lines of constant elevation, and the spacing between the lines gives you an idea of how steep the landscape is. The more contour lines over the same distance indicates a steeper slope. Areas with widely spaced contour lines are gentle slopes. Picture yourself on a terraced farm facing the peak. To your left and right will be the directions of constant elevation, and walking this contour will not get you further up nor further down the hill. Let's look at the concept of the algorithm. We already have the gradient vectors, and we have the surface normal. The gradient vectors are tangent to the surface. So performing a cross product between the gradient and the normal will give us the contour lines. By definition, the velocity vector must be tangent to the contour line. When moving along a contour line of the function, the value of the function neither decreases nor increases. And so the dot product of the velocity vector, in example the vector along the contour lines, and the gradient vector must be 0. As such, the gradient vector must be perpendicular to the contour line in order for the dot product to equal 0. While the gradient vector field is curl-free, the velocity field computed from the contour lines is divergence-free. You can easily see this when you look at the gradient vector fields, that there is no rotational part. And we will soon see when we look at the contour lines that there are no sources or sinks in the vector field. Just knowing these simple facts will unlock so many possibilities, because you gain an intuitive understanding of these fundamental concepts. You will be free to combine these and create really interesting effects. Let's implement this in Houdini now. We will use the previous scene, as we only need to change a few things. Duplicate one of the branches. Create a wrangle node to perform a cross product between the gradient vector and the normal, after the gradient vector is computed. Instead of using a hard-coded attribute for the gradient, we will create a string parameter. We will also allow turning of the cost attribute. This is especially important with contour lines, as the cost attribute along the same contour line would always be constant, and as such would lead to premature termination. Just organize the parameter interface a bit. As you can see, we have successfully traced the contour lines. In terms of look, you have so many ways to control it. As far as point density, you can either have a lot of points with relatively shorter length, or a lot less points that travel a lot longer. Or you can do both at the same time. Both looks are very interesting. I will also merge the original grid to occlude the back-facing curves. I will also merge the gradient ascent and descent separately, and also together, to see how everything looks when combined. It is a network of curves when you combine all three. I think the density of gradient ascent and descent is overpowering the contour lines. When you use very large max list, it looks like capturing car lights using extended shutter time. You can also see how this field is actually divergence free. There will be no sources and sinks present in contour lines. You can also experiment with the uniform distribution of points versus having a non-uniform distribution. Another way to control the look of contour lines is by adjusting the attribute blur nodes. As the deformed grid becomes smoother and smoother, so does the contour lines. Blurring the gradient has the same effect, except more on the directionality of the contour lines. When viewing from the top, you see a contour map, similar to landscape contour maps. We will now apply the same thing on a 3D geometry. This time, I will use the Victoria Angel model. So just copy-paste the wrangles that has the cross product and the contour lines code. We have to adjust the parameters to conform to this model and merge the peak version of the original model. You can see it works perfectly here too. It looks like a glowing hot, super reflective model. I'm just gonna play with the same settings to show you some variations, so you can get a better intuition how everything plays together. When we blur the cost attribute, we are losing more and more of the general shape of the geometry. When the blur is so high, the entire face area looks like she is wearing a veil, like Lady Justice, which is pretty cool. And of course, you can have different amounts of blur at different parts of the geometry. In the next video, I will show you how to apply the same concepts to a height field. And with that said, see you guys in the next lesson.